Last class, we learned about the equilibrium constant expression, and we learned that this expression and this constant are determined from the balanced chemical equation, and the actual value of the constant is determined by experiment. In some cases, we will be able to determine an equilibrium constant not by doing an experiment, but by manipulating a previously known reaction and using its equilibrium constant. For example, if we look at this equilibrium here, PCl3 plus Cl2 in equilibrium with PCl5, we can see that the equilibrium constant is PCl5 over the concentration of Cl3 times the concentration of Cl2. Now, if we change the direction of this equilibrium, so essentially we reverse this equilibrium to become PCl5 in equilibrium with PCl3 plus Cl2, what we can see is that the new equilibrium constant expression, concentration of Cl2 times the concentration of PCl3 over the concentration of PCl5, is simply the reciprocal of the original Kc expression. So therefore, if we know the value of the original equilibrium constant, so for example, if it were 10, then what we could do is, rather than setting up a new experiment to determine the equilibrium constant of this new equilibrium, we can actually calculate it as being equal to 1 over 10. Simply the reciprocal of the original. Another manipulation that we can do is to actually multiply a reaction by some coefficient. So if we take this original reaction, PCl3 plus Cl2 in equilibrium with PCl5, and we multiply the entire reaction by 2, then what we can see when we write out the equilibrium constant expression, that it's PCl5 squared over concentration of Cl2 squared times the concentration of PCl3 squared, which, if we examine it carefully, we can see that it is actually simply this equilibrium constant expression, all squared. So from this, we can see that if we multiply by some factor of x, then what will happen to the equilibrium constant is it will be raised to that power. So for example, in this case, the new equilibrium constant would be 10 squared. We're going to raise it to the power of what we multiplied the reaction by. In another scenario, perhaps instead of multiplying by 2, we would multiply by 3. The equilibrium constant would therefore be 10 to the 3 in that case. Whatever you multiply by is what you raise the equilibrium constant to get the new value. A third kind of manipulation that we will work with is adding chemical equilibria. And in this case, what we're going to do is we're going to prove that if we add two equilibria, what will happen is their equilibrium constants will simply multiply to get the new equilibrium constant. Now, first of all, we have to go over what it means to add reactions. And what we're doing is we're looking at these two reactions, and we're going to add them to become this third reaction. So we can think about it as a big plus sign. Okay, so we're going to add these reactions. Now, what we need to do is to look at all of the reactants and all of the products, and we're going to take the sum. So one way to organize this is to take all of the product. So I've got reactants, right? 2N2 plus O2 plus 2N2O plus 3O2. Okay, and this is in equilibrium with 2N2O plus 4NO2. What ends up happening is once we've combined the reactions like we just have, then we're going to group like terms. So this is essentially the same as adding two linear equations, right, or mathematical equations. So what we can see here is we can combine, so the O2 and the O2 will combine to make the 4O2. The N2 has nothing on either side of the equation to simplify. And then the N2O, if you look at it, you've got 2N2O on either side of the equation, so this can simplify, okay? Just like it would in a math equation. So those will simplify, and we're left with 4NO2 as a product. So this is actually the mechanics of adding the two reactions. And now let's look at the equilibrium constants. Like I said before, if we add two reactions, what we expect to happen is that the equilibrium constants should be a multiplication of the two. So let's look and see if that works. The first equation, the Kc, is N2O squared over N2 squared times O2, while the second equation is NO2 to the 4 over N2O squared times O2 cubed. If we take these two expressions, as you can see at the bottom here, we take these two expressions and we multiply them and treat it algebraically. If you take a moment, you'll be able to see that what you're left with is this expression here. And if you look at that expression, it is the Kc value for this third reaction that we created. So NO2 to the 4 over N2 squared times O2 to the 4. Now at the moment, this seems like a mathematical process that we're dealing with. But what we're going to do next is do some examples so you can see how this might be useful. So with these practice examples, in the first reaction that we're given, we know the Kc value. So this Kc value was determined by completing an experiment. We look at it, and it's H2 plus F2 in equilibrium with 2HF. The question asks us to determine the Kc value of a couple of different reactions. So the first one being half H2 plus half F2 in equilibrium with HF. What we need to do in order to determine the new Kc is to first decide what kind of a manipulation was done on the equilibrium. If we compare the original equilibrium to this equilibrium, what we can see is that it's showing up in the same direction, but it's been multiplied by 1/2. Okay? All of the coefficients have been multiplied by 1/2. So we look to our rules. The rule is that if we multiply by some factor of x, the new Kc is equal to the original Kc raised to that power. So I'm going to raise it to a power of 1/2, which is equal to the square root of 115. When we do the computation, we find that that's equal to 10.72. Let's look at the second example. And we'll always compare to the original, for simplicity in this case. If we look at B, what we can see is that the reaction has been reversed from the original, and it has also been multiplied by 1/2. So there have been two manipulations. So when we calculate the Kc value, we need to apply both of those manipulations in order to determine the new Kc. The first manipulation of reversing the reaction calls for the reciprocal, because as we saw from the note, when we reverse a reaction, the value of the Kc becomes the reciprocal. So it's 1/115. Again, we multiplied this reaction by 1/2. If you multiply a reaction by some factor of x, then the Kc value gets raised to that power. So we raise this to the 1/2. When we do this computation, what you find is that you get 0.0933. In the last example, comparing it to the original equation, we can see that it was both inversed and it was multiplied by 3/2. Okay, so because it's been inversed, flipped around, get 1/115. Because it was multiplied by 3/2, it gets raised to the 3/2. And what we are left with is a value of 8.11 times 10 to the -4. So those are some straight manipulations, and it is important to be able to do those manipulations. The next problem that we're going to look at is going to show you how all of this can actually be useful. This is the kind of problem that is quite common. You're given the equilibrium constants for a series of reactions. In this case, you're given the equilibrium constant for this reaction and the equilibrium constant for this reaction. Our goal is to be able to determine the equilibrium constant for this third reaction. So the way that we're going to do that is by figuring out a way to make the first two reactions add up to the third reaction. And we're going to use a combination of the manipulations in order to determine the new Kc value. The process of doing that is to look to our goal reaction and to see how the previous reactions can help us. Our goal reaction is to have NO plus half O2 in equilibrium with NO2. So what we do is go through this reaction, one molecule at a time, and look at which reaction is going to help us to achieve this goal equilibrium. So the first one, we've got NO. We look to the two reactions. It's the second reaction that has NO in it. What we need to do is ask ourselves two things. One, is the NO in the correct position? And does it have the right coefficient? When we look at this, we can see that the NO is not in the right position. In order to get it into the right position, we will need to flip this reaction or reverse it. We also see that the coefficient is incorrect. In order to get the coefficient that we want, which is 1, we'll need to divide by 2. Okay, so we've made a decision about the manipulations that we are going to do on our second reaction. Then we come across the O2. The O2, being part of both of the reactions we're dealing with, isn't very helpful. So we're going to skip over that one and look to the NO2. The NO2, you'll see, is in the first equation, and we ask ourselves the same two questions. Is it in the right position? Yes. And does it have the right coefficient? Yes. So in this case, no manipulations will need to be done. So step one, really in this entire process, is to make those decisions that we've just made about what kind of manipulations we'll need to make on the initial reactions. The next step is to actually do the manipulations and to write out the reactions. So I'm going to write out the reactions here. The first one, I didn't need to do any manipulation, so I'm simply going to write it out. Okay, I'm writing it out again because it's going to help me later on with the adding process. Okay, we need a 45 there, and I'm running out of room, so I'll just put a little blob, but there should be a 45 there. This one, next, I've decided that I need to flip it, and I need to divide by 2. So what I need to do is perform both of those changes on the reaction. So I'm flipping it around, so the NO becomes the reactant, and I'm also dividing it by 2, or multiplying by 1/2. So my new reaction becomes NO in equilibrium with 1/2 N2 and 1/2 O2. Because I made this change, the equilibrium constant is also going to change. And we need to apply the appropriate manipulations. So we flipped it, so it's going to become 1 over 1 times 10 to the 60. Okay. And we multiplied it by 1/2, so we need to raise it to the power of 1/2. So these two equations should, when we add them, should equal the goal equation, which we are trying to achieve. Okay, so the goal equation, if we look at this, we've got N2 on both sides of the equation, so those will simplify. We've got O2 on the left and 1/2 O2 on the right side of the arrows. So what we will be left with here is NO plus 1/2 O2 in equilibrium with NO2. What we learned previously was that if you add two reactions, the equilibrium constants get multiplied. So the equilibrium constant for this third reaction, our goal reaction, is equal to the equilibrium constant 1 times 10 to the 45 multiplied by 1 times 10 to the 60 after it's undergone this manipulation. So it's going to be 1 times 10 to the 45 times 1 over 1 times 10 to the 60 to the 1/2. And when you do this math, you get 1 times 10 to the 50. The key with being able to do these is to do practice questions. Okay, so hopefully you will complete the practice 14.7 on page 625. The next piece of this lesson is to look at the magnitude of K, okay, and the significance of the actual size of K that we're dealing with. Let's consider these two reactions. First of all, let's consider the reaction of forming water molecules from H2 and O2. If you've ever done a hydrogen test where you add a burning splint to a sample of hydrogen, you'll remember that it makes the sound pop. Okay? This is actually the reaction that's happening in that case. The hydrogen is reacting with the presence of a spark with the oxygen in the air. And if you ever look really closely, you'll see condensation forming when you do a hydrogen test. Now, this reaction happens with a very large value of K. So if we look at the K expression, it's H2O squared over H2 squared times the concentration of O2. The value of this K is 9.1 times 10 to the 80, okay, which is a very large value of K. Okay, I hope you can appreciate that it's a large number. If we look at this, the expression that we're dealing with here gives us the relationship of products over reactants. So by seeing that we've got a large K value, we can connect that and see that at equilibrium, the concentration of the products must be significantly higher than the concentration of the reactants. So essentially, this reaction goes to completion, or very, very far to the right. The products are highly favored in this equilibrium. Similarly, if we look at this reaction of nitrogen and oxygen to produce NO, the value of Kc for this reaction is 4.8 times 10 to the negative 31, okay, which, as you can appreciate, is a very, very, very small number. So if we look at the relationship of products over reactants, in this case, the small k is telling us that the reactants are in a much greater concentration at equilibrium and therefore are favored. So really, this reaction doesn't go very far towards completion at all. This is a really important concept because you shouldn't be thinking that because something's at equilibrium, the products are equal to the reactants. Okay? That is not the case. Yes, the rate of the forward reaction is equal to the rate of the reverse reaction when there is an equilibrium, but the actual amount of reactants and products don't necessarily need to be equal, and in most cases really aren't equal to one another. Okay, so to summarize in this chart, if you've got a large K, it means the reaction proceeds towards completion. If it's very small, we hardly get any products at all. And if it's equal to 1, the concentrations of reactants and products are essentially equal to one another at equilibrium. At this stage, you were able to complete, and should be able to complete with confidence, the Equilibrium 1 online assignment.